So, hello everyone again and welcome to my channel. In here we'll be looking at enzymes and one of the properties of enzymes. This is going to be a long video. I'll try and make this short and sweet. We're going to be looking at selectivity and how enzymes are able to actually pick up their reagents and influence the way they are able to actually make their final product. And now this selectivity comes in various ways, and there are actually three ways by which they influencing the substrate to transform into a transition state and get our final product. Now, one of this particular selectivity is called chemical or chemoselectivity. And chemical or chemoselectivity is quite interesting because in here we're looking at enzymes that can discriminate between functional groups. Let's take for an example. We have this particular reagent where we have an ester over here, and we're trying to look at how this ester can either react with this particular functional group, which is an alcohol group over here, or it could actually react with this other functional group, which is an amine functional group over here. One interesting thing about this is that in nature we tend to go to a much more basic condition, and this particular functional group here is much more basic. Now, since it's much more basic, then you expect this particular pathway to actually go properly. However, if you include the enzyme, a particular enzyme by the name of lipase, this is kind of a fatty enzyme or so, but it is also made from protein, right? So what this enzyme does is that it tries to actually move the reaction away from the amine functional interaction over here to more of the hydroxyl interaction over here, which is actually the alcohol. So this pathway is highly favored in the presence of this particular enzyme to get to our product, which is of this particular nature over here. And take note that I'm having this interesting stereochemistry over here, and we're going to talk about the stereochemistry part later on in this particular video. So this is our product, and we get 100% over here compared to the other product, which is just over or just one compound being formed out of 100 compounds being formed from the particular hydroxyl interaction with this particular ester over here. So that is for the chemoselectivity. And taking note about this, the reason why this is much more basic is because, or I might say it's because it's much more nucleophilic, because that would be a better way to actually explain the reason why in nature you most likely go through here. However, in the presence of the enzyme, you actually go through this particular part over here. So most especially in a transacetylation reaction, the lipase prefers this particular process. So this particular reaction that this particular lipase actually takes the reaction to is called a transacetylation reaction, and by that way you're able to fuse this particular hydroxyl group over here into here, forming this particular cleavage of this bond to form this particular product over here. So the next one is regioselectivity. And regioselectivity is another type of selectivity that enzymes usually perform while they're trying to transform their substrate into the final product. And in here we'll be looking at enzymes that can discriminate between equivalent functional groups located on different regions of the substrate molecule. So it's kind of interesting because we look at various species, and most species they usually have pretty much the same functional group, and how are they going to be able to look for regions where they can actually cleave from or actually fuse. Now in here we're going to be looking at this particular enzyme by the name of catechol, and there are actually two forms of this catechol. We have one that actually attacks in the 1,2 position, or I'm actually do this because for a better discrimination, dioxygenase, or we have the other one over here, which is catechol attacking in the 2,3 position of our particular reagent over here. Now, the reagent that will be in focus is this particular reagent over here, and this reagent has two adjacent hydroxyl functional groups over here, and what we got is this benzene ring, and we know that benzene ring is really hard to actually cleave off, but this enzyme really makes this particular process really easy. And now in the presence of oxygen, you can be able to transform our reagents to one or two ways. The 1,2 position actually cleaves the bond over here. I'll make this green to make this kind of look more colorful, and cleaving the bond between the 1,2 position makes way to be able to form our particular product, which is kind of a beautiful structure because it has a nice conjugating system, and the nice conjugating system makes this particular electrons over here to flow really well due to the nice orbital overlap between the pi bonds. And you got this particular compound over here when you include this particular enzyme in the system. However, if you include this particular enzyme into another system, you arrive at a different product. And what we have here is that there's an attack between 2 and 3. So if I do a positioning over here, I make this by 3, so there'll be a cleavage over here, and what I get is the formation of our particular product over here, where you have the hydroxyl not further apart but pretty much close together. And over here we also have a nice pi conjugating system, but noting that there is actually 2 carboxylic acid functional groups over here. However, we just have 1 carboxylic acid functional group over here, and in here we have an aldehyde, and in here we have a kind of an enolate here. So pretty much fascinating to see this come into play. And last and foremost, stereoselectivity is the last selectivity that enzymes usually take into consideration before reacting with our substrates to form our final product. Now this stereoselectivity looks at how enzymes discriminate between stereoisomers, and most importantly you need to note that most enzymes or all enzymes are chair or chiral, which means that they actually favor one particular enantiomer. And one of the most interesting things is that most of the reagents that are in nature, they usually have 2 forms. The racemic mixtures are usually generated mostly when you have an in-1 reactions. And what does racemic mixture mean? It means that you actually make 2 products that have a stereocenter that is actually one opposite from each other, either in the Fischer projection where we have our D or L, which are 50% being made, with 50% being made over here, or we have our R and S, or R and S being made, that you have 50% being made and the other you have 50% being made. Really hard to actually separate these 2 enantiomers. However, with the presence of an enzyme focuses more on one of the particular enantiomer and actually reacts with it, because enzymes are chiral. Now, let's look at an example of this particular case. One example of enzymes that actually perform this particular process is called the amino acid oxidase. And what does this particular enzyme do? It actually oxidizes the D amino acid form, but it doesn't act on the L. By that way, you can separate the L from the reacted D amino acid in this particular case. However, on the other side, we have another enzyme which focuses on the other enantiomer, which is the L amino acid oxidase. What does this do? So I forgot my E on the other one. This other one, what it does, it oxidizes the L enantiomer of the amino acid. That's about it for this particular subject over here. In here we've seen the 3 types of selectivity that enzymes usually perform anytime they are about to react to with a particular substrate to form a target product. And it's kind of nice to see how chemoselectivity, we have regioselectivity, and lastly stereoselectivity all plays a key role in identifying and also forming various products in organic chemistry and also in enzyme chemistry. All the same, guys, thanks for watching. Please don't forget to hit the like button, share and subscribe, and let me hear your thoughts about this particular topic. Did you find this interesting? Do you have any questions? Please hit the comments and let me hear about all of them. All the same, guys, thanks for watching. See you on my next video. Bye.